Thanks for introduction. Hello, everyone. I'm Taro Sekiyama. In this talk, I'm going to present the space-efficient implementations of a polymorphic gradual typing is possible if the polymorphism is restricted to be mostly parametric. Okay, so first, let me introduce what is a gradual typing briefly. Gradual typing is a type methodologies to enable the migrations between static and dynamic typing. And to do so, gradual typing introduces a special type, star, which is called the dynamic type. So the specialties in dynamic type is that the type check for the dynamic type is skipped at compile time, but instead it is deferred to the runtime. So okay, so let's see one example here. Here, the successor function takes a value of a star, but it is converted to the integers, and then the successor of it is returned as the value of star here. And as I said, the static type checking for star is skipped. So both of our two function applications in below are well typed. But such a type checking is deferred to runtime, which means that the Boolean value in the second function applications, it is checked that the Boolean values can be used as integers at runtime. But of course, it's impossible, so a runtime error happens if such a type mismatch is found. Okay, and if the types of successor functions is turned to be more static, like int to int, then the type checking is shifted from dynamic checking to the static checking. So then we can find the second application is ill-typed. Okay, and this is a very brief overview of gradual typing, and there are many theoretical extensions of gradual typing. And in this talk, we focus on the extensions of parametric polymorphism. Okay, and the parametric polymorphic gradual typing is an extension of a gradual typing with a parametric polymorphism, and it supports universal types as usual polymorphic languages. But the distinctive point of polymorphic gradual typing is that it enforces parametricity at runtime. So parametricity is a crucial property of polymorphic languages. It ensures polymorphic values behave uniformly, independent of how polymorphic values are instantiated. And in the polymorphic gradual typing, the parametricity is checked at runtime. So it means that if programs try to break the type abstractions given by polymorphism, then some runtime errors happens. Okay, let's see one example. So here, ID star is just identity functions, and it is converted to the polymorphic identity functions through star dynamic type. So then ID star can behave independently of arguments. So it can be used as a polymorphic identity function. There's no problem. But if some successor, for example, successor functions is used as a polymorphic identity functions, it is possible by using dynamic type. Then the successor functions, the behavior of a successor function depends on the argument. So what argument is given here? So then the runtime enforcement of parametricity ensures that, okay, this function accesses concrete values of the argument, then runtime error happens. So then it can prevent the argument-dependent behavior. And of course, similarly, if the functions tries to dynamic analysis on type argument, then runtime error happens. So in this case, variable x has an abstract type big X, and then x is converted to the integers through the dynamic type. But such conversions breaks the type abstraction given by the polymorphism. So all of the function applications triggers runtime error, also in this case. Okay, and our long-term goal is to, okay, so many theoretical aspects of a polymorphic gradual typing has been studied so far, but our long-term goal is to obtain the efficient implementations of a polymorphic gradual typing. But to do so, there are many open questions. So in this work, we focus on one question, whether space-efficient implementations of a polymorphic gradual typing is possible or not. But unfortunately, in general, polymorphic gradual, parametrically polymorphic gradual typing cannot be implemented space efficiently. It is a known fact. But our discovery is that this is not the end of the story. So in this work, we show that it's possible to implement the polymorphic gradual typing space efficiently if polymorphism is mostly parametric, not a free parametric. So here, most parametric means that parametricity is dynamically enforced only if polymorphic values are instantiated with non-star types. Okay, so let's see one example to find the difference. So here, this is an example that converts the successor function to the polymorphic identity functions. So as I said, in a freely parametric semantics, both of the function applications lead to the runtime errors. But in a mostly parametric semantics, only the first function application raises the error. Because in the second applications here, the type argument is star. And in mostly parametric semantics, in this case, parametricity is not enforced. Okay, so in this case, the argument is just a pass to the successor functions and return the value returned by the successor function as it is. Okay, so then next, so this is an overview of our work. So next, I will talk about why this restriction on polymorphism can lead to the space-efficient implementations. So to explain it, first I need to explain the coercion calculus, because space efficiency is properties of intermediate language in gradual typing. And coercion calculus is one of the intermediate languages, and there runtime type conversions appear explicitly as coercions. Okay, so for example, let's consider one example here. This is a program in the surface language, and here number 42 is converted into line, and then x has a dynamic type, but x is used as integers, so it's also converted from the line to in here. Okay. And this program is represented in coercion calculus like this. So here are two coercions. So one thing comes from the conversion from the into star. And this coercion we call the injection coercions here. And the second coercion is into question. It comes from the conversion from star to static type. This program behaves like this one. So first, this projection function, injection coercion just attach the type tag to the value. So then 42 into bang is just a value with type tag int. And then x is replaced by the quotient injected value. But here into question checks the tag in the projection function. The tag in the int questions is the same as the tag attached to the argument value here. So in this case, the two quotients have the same type tag, so the check successful. But if the integers, 42 number is replaced by the Boolean value, then the type mismatch happens, so then it leads to the runtime errors. Okay. And so this is a simple behavior of a coercion calculus, and we extended this coercion calculus to a parametric polymorphism. So to do so, first we introduced the notion of type names, which has been introduced by the previous work on polymorphic gradual typing. Yeah, and type names okay, so type names are generated to evaluate type applications. And this is the evaluation rule in our calculus for type applications here. And to evaluate this type application, first a fresh type name alpha is generated. And then bound type variable x is replaced by alpha. The intuitions to understand this rule is that one of the intuitions is that type names can be considered as fresh base types. And type application generates fresh base types alpha. And we also introduced 4 kinds of new coercions to allow the interaction with star. The first is for injection and projection for type variables, and the second 2 are projection and injection and projection for type names. But the notable point here is that the types of coercion for type names are a bit non-standard. So here, type A corresponds to the type argument, that type argument of the type application that generates type name alpha. Okay, so in this case, alpha, the type of A corresponds to this type argument here. Okay, and these 4 type names and coercions can enforce the parametricity at runtime. Let's see one example here. So this is an example that does a dynamic type analysis within the function body. So then this program is represented like this one in coercion calculus. So here x bang and so on is inserted. First, okay, so then let's evaluate these function applications. First, type applications is evaluated. So a new fresh type name alpha is generated here, and x is replaced by alpha. And but here x prime is replaced by 42 alpha bang. So then into question checks the 2 type tags the same, but alpha and int are different. So here random error happens. So this is why we can consider type names as a fresh base types. Okay, and okay, so next let's consider space efficiency. So very briefly speaking, space efficiency means that the space consumed by coercions at runtime is statically predictable. A bit more precisely, it means that if a consecutively applied coercion appears at runtime, then such coercions can be compressed into a coercion whose size is bounded statically. Okay? So then, by keeping in mind this notion of space efficiency, we can show that the impossibility of space-efficient implementations by using the 3 facts. The first fact is that we can provide a program that generates coercion sequences that consist of injection coercions for n different type names. And the second fact is that the coercion sequence cannot be compressed into simpler coercions. And the third factor is that the size of this coercion sequence is not less than n. So using these facts, we can find we can find for any n, the program may generate can be evaluated to program state where the space over coercions may be larger than n. So then space efficiency doesn't hold in the freely parametric polymorphic gradual typing. But from these counterexamples to space efficiency, we can have key observations. So the first one is that the problematic coercion sequence is well typed only when, for every type name alpha, the injection coercion has this type start to stir. And the second observation is that such a type name alpha I is generated by type applications with star as a type argument. By using, okay, so then we can say that the impossibilities is due to the type name generation at type application of this home here. Then conversely, we can show that space efficiency is possible if the type applications with star as a type argument generates no type name. This is our observations. Okay, let me summarize what we achieved formally. So we provided two coercion calculus, so lambda C and lambda S. And both calculus employs mostly parametric semantics, and we show that parametricity holds on the first coercion calculus, lambda C. And lambda S is equipped with space-efficient semantics, and actually, we show that it actually satisfies the space efficiency. But to do so, we also introduced new coercions, which is necessary to represent type analysis on whether type argument is dynamic or not. But I skipped the details in this talk. Okay, this is all of my talk. Thanks for listening.
We have time for a few questions.
Hi, my name is Jeremy Seek. My question is about the restriction from sort of a practical standpoint, thinking about like when we would be using parametricity, maybe to prove free theorems or stuff like that. Do you see the restriction as, or do you foresee it as something that would get in the way of people using free theorems, or is it like no big deal? I mean, I think I know the answer, but I'm curious, like your thoughts on that.
Yeah, thanks. Yes, it's a very important questions, especially for applications. Yeah. So I'm not so familiar with the compiler techniques, but I hear that free theorems parametricity can provide many free theorems, and free theorems are very useful in the compiler optimization. It is one thing. And the other thing is that parametricity can be related to the security verification, like a non-interference. So if we apply such a technique in a gradually typed setting, then I think parametricity is totally important. But I'm not sure this mostly parametric polymorphism is still useful for such a context. So we need to explore.
Sure. I mean, I think, yeah, you're being humble. I think I think in a lot of applications of parametricity, you're going to be wanting to use specific types to instantiate. So I envision that this restriction is not all that hard of a restriction, that in many cases it'll be just fine. So.
Yeah, thanks.
Okay, let's thank our speaker.